you did. I thought we had to defuse a bomb. What's going on?
6 o'clock. 6 o'clock.
Walking to my shop.
I kind of learned a little bit.
Yeah, that's it. Where are the boys?
Boys? Boys? I'll turn down house music after. Megan.
What?
I think your next director of Astro on Tap should also you can make a strategic decision on whether or not you want the Astro on Tap to continue to be bastardized or not.
To be bastard.
What?
What does that mean? What does it mean?
I stand by my statement.
What?
I stand by my statement.
Yeah, I stand by your statement. Me personally, I like being a good bastard as astronomy on top.
What was the poll in that?
Microphone.
I thought you were like showing us a
Off the
tattoo.
record. This isn't prison, Jake.
I've said words so
Sam, someone else went to prison this morning.
I went to prison this morning.
Well, Sam, people in this circle.
It says excellent connection, so I think we're fine.
Yeah, I'm happy.
Do we have the little clicker? Oh yeah, where's the clicker?
Just your his own though, if you want to.
Oh, you want to use your own clicker?
Sam Carney knows that we have 2 clickers, and Colloquium does not have a clicker.
I mean, we could just plug
It's
it in and use
proposed
that.
Colloquium.
Ah.
And it's proposed that we donate 1 to Colloquium.
What has Colloquium ever done for us?
Send
Yeah.
us one-
Yeah.
The rocket guy. Remember the rocket guy? UV rockets?
True.
Oh yeah, that's true. This is fancy. That's true. Sam. What? Keyboard setup assistant.
The guy who took questions in the middle.
10-minute rocket.
The other one doesn't do this.
It just it's not used to it.
This? What? Immediately to the right of the keyboard, what is it? This? To the right of the shift key. I don't have any keys to the right of, I mean this one. Okay, fuck it, we're not doing this one. Yeah. Sorry. Okay, Colloquium can have this one. It doesn't work. Yes. We can't use this one on my laptop. Oh, just kidding. It's Chester's. Colloquium can't have that one. No, we're gonna do this one. Okay.
Wait, this is not mine. Oh, wait, no, sorry. That was the wrong one.
Chester!
This is the USB.
Okay, we're gonna use that one. We're already gonna do that. We're gonna do that one. It's already happening. It's like, what is it?
That was the wrong USB. That's fine.
I don't understand. Alright, one more call for trivia. Okay. Give me a sheet.
Hello everyone! Once again, welcome to Astronomy on Tap. Just want to remind you, if you want to play trivia with us, we're about to get started. You can get a trivia sheet and golf pencil from Sam at the front if you haven't done so already. And we got new prizes.
And new prizes.
Thank you.
Fresh off the press.
New prizes.
Hey Ben, long time no see, man.
Oh yeah, Hashik told me that you saw you earlier in the conference or something. Remember who Hashik? Data breaks.
I'll look at it later.
Do we have answers? Is that what you said?
No, we don't. No, we don't. Okay, that's true. We'll figure it out. We'll figure it out later. Me too. Okay. Come on, are we ready to go? I'm on it. Yeah. My friends? Trivia sheet?
Wait, what does that say? It said YouTube is not receiving.
Am I good to get started?
We dropped one.
Okay.
1 minute. We got plugged in.
Yeah. I know.
I think.
We're good? Okay, trivia?
I'm not. We can flip this while the trivia is going. And if it's not, if we can't get it up by the time, we'll try it. But I think we try it.
All right, we're going to go ahead and get started at this point again for the third time. Thank you for coming to Astronomy on Tap. Tonight, we only have one speaker, but it's going to be a great talk. We're going to hear from Chester Lee about the artificial intelligence era of astronomy, which is upon us all. But before we get started, there's a couple of things that I want to announce. I guess number one, next Astronomy on Tap, you can mark your calendars. It's going to be February 26th. The second thing I want to announce is that the astrobiology program at the University of Washington has organized a 25th anniversary lecture series. This is free, open to the public, for a general audience. It's going to be across the first 4 Wednesdays of April, all at 7 p.m. at Kane Hall on the University of Washington's campus. You can get tickets at this link on Eventbrite, and these are our wonderful speakers that we're going to be having visiting us. So I'll leave that up for a second, but it would be great to see all of you there. Great. I'm just leaving it up for the QR code. Okay, the other thing I wanted to announce, and you probably saw this on our social media, we are trying to get a new projector for Astronomy on Tap, specifically for the summer months. Yeah, I know. A lot of you that have been with us for a while know how difficult it can get to see the screen once the sun starts staying up into 9 p.m. So we are currently raising money to try and buy a new projector. Please don't feel pressured to donate, but if you can, that would be wonderful. Depending on how much money we're able to raise, we might also end up putting in grant proposals to try and supplement it. You may or may not know, but we're completely unfunded here. This is all volunteer time and work, and equipment that we get is also usually donated. So we're going to do our best to get a good system going. But you'll see this QR code, again, probably posted on our social media in the next few weeks too. Okay, so with all of that being said, we're going to get started with trivia, astronomy and AI trivia. I hope you're all ready. How this works, in case you haven't played it with us before, I'll put each question up on the screen for 30 seconds apiece. At the end, I'll go back through and show every question again, but only for 15 seconds apiece. So you'll get 2 opportunities to write all of your answers down. After trivia is over, we'll collect your sheets and grade them during Chester's talk. Okay, ready to get started? Yeah! Very enthusiastic. All right, let's go. Oh, you made it. You made it. Thanks, it's cold.
Little corn on your.
So fast and steep.
Before, and they haven't had to actually look at it.
Cider?
Non-alcoholic hot cider.
Classify spiral galaxies from non-spirals? Or classify them into subcategories?
I think just to like say if they're spiral or not. I think. It was part of like a training thing when I was in undergrad of like people finding galaxies and trying to find polar ring galaxies, and so it was like thousands and thousands of images. It was like this would be like this. This is before the age of AI.
What true positives do you use for training studies?
What?
What true positives do you use? Some false positives? Use true positives.
No, we only use objective.
You make some text.
Synthetic sources. No real data yet.
We've heard this before many times.
What's the answer?
You should know this. You're
I know the
illest
answer.
guy.
He's testing you.
I know the answer. I think it's between two of them.
Testing you. How many asteroids are we using each year?
Each year? 450,000. But most of them in the start. Like first 2 or 3 years, you cover pretty much the whole sky.
Oh, right.
So you get like 80%. It takes another.
But the peak is going to be 150,000. The peak.
At the very end, it'll be 5 million. And so half a million a year. Went back to
I fixed it.
moral of the story.
Okay, I'm going to go through all the questions one more time, but faster this time, so hopefully you'll get all of your answers down by the end of this round.
Oh yeah. Like the whole internet across the world.
I'm like that. I'm like that.
On that grind.
Well, you studied astronomy. Nobody studied the images.
You could call me machine learning because I've been doing a deep dive on that.
Topical too. Oh. I'm gonna run it down.
The Ethernet,
Because Ralph broke it.
which is yeah, we like to say Jake broke it and Toby fixed it. It's kind of our theme here at AOT.
When I break things, I just say Andy did it.
CCF watching.
These guys can watch most of it.
How many people are on the live stream?
6? Oh,
Oh, he's on the.
I can't find his. I just posted the board.
Dude, he's got a sexy smolder on his face. Look at that. Big old sexy smolder. Man's on. He's standing on business.
I think that doesn't deserve maybe to say after yourself.
Chester, you ready? You ready? Are you mic'd up?
Okay, if you all have your trivia answers down, please bring your trivia sheets and golf pencils to Sam down at the front. Please return the golf pencils. Maybe if we have leftover money, we'll buy pens.
That wasn't a joke. That's just the truth. Oh, right. This is okay.
Ask you a quick question. If my friend has a really nice projector that he never uses, can you download it?
Yes, he can.
Cool.
Well, we will be grading the trivia sheets during the first and only talk. But without further ado, it's my pleasure to welcome Chester Lee. Chester is a PhD student in the University of Washington's Astronomy Department. Chester is working on machine learning techniques and their application to the Verisi Rubin Observatory and the LSST survey that's going to be coming online hopefully later this year. Later this year? Yeah, later this year. So please welcome Chester.
Hello, everyone. Welcome to Astro on Tap today. So my name is Chester Lee, and I'm going to be talking about the artificial intelligence era of astronomy. And I see a lot of tech brother and sister in the audience here. So if you please point out my mistake and the bullshit I say during this talk at the end. And I know I'm going to say a lot of wrong things, but just keep in mind and humiliate me at the end. Okay, so I am studying astrophysics, astrobiology, statistics, and a lot of things at UW. And some past research experience I have is detecting streak-like asteroid with AI and also dark matter subhalo simulation with AI. Those are the two things that I will be talking about later on during my talk, which is like how AI can help contribute to the research in astronomy. And also, I'm proud to say that I'm the president and founder of the Data Science Society at UW, which we hope to bring people together who are interested in machine learning, data science, And this is a symbol that we have, which is kind of cool. But without further ado, let's dive into today's talk. Okay, so recently, who has seen AI on their social media, the word AI? Okay, a lot of people. Okay, so AI has really been this really popular and hot topic recently in all of the news. And this is, I'm just doing a quick AI news search on Google. And this AI stuff is really hot. So why don't we use it for astronomy, right? But before we talk about astronomy, I want to give you a brief history on the development of AI. So it all started in 1943 when McCulloch and Pitts proposed the first mathematical model of a neuron. So they were not computer scientists. They were psychologists, or whatever you say it. But the thing that they proposed is that this neuron could be something that takes in information on the left here and output a 0 or 1, which is like you're thinking about a brain cell acting as a switch. It can be turned on and off. And on the left here is a diagram of what a neuron should look like. So even though this was not related to computer science at all, it really laid down the groundwork for artificial intelligence that we think about today. And next, we're going to talk about this man, Alan Turing, which is considered to be the founder and the father of modern computing. And in 1950, he proposed this test called Turing test in his paper. What it is talking about is, so it's asking a central question: can machines think? So he proposed this kind of a thought experiments. Imagine a human in here only communicating through text with a computer labeled as A and a human labeled as B. So the test is to figure out, can the human here figure out which one is the computer? So far, none of the current algorithm has passed this Turing test based on what I know so far. So what this test is telling you is, can a machine be indistinguishable from a human? And if a human cannot tell is the text is coming from a machine, then his machine is doing a pretty good job in mimicking a human behavior. And next, we go to this 1956 conference on AI. And it took place in Dartmouth University. And it was later called, right now we call it the Dartmouth Conference. It was such a pivotal moment because the organizer bring together a lot of people together, basically to investigate the potential of creating machines that can simulate human intelligence. And the term artificial intelligence was first coined there in 1956. So it was really an amazing meeting. And here is a photo of the meeting that took place. And let's move on to some early developments. So some of you may have seen this in the 1966. The first chatbot, one of the earliest chatbot called Eliza chatbot was invented. What it can do is it can mimic a psychotherapist and answer some questions. But the thing is that all it does is doing some pattern matching. It doesn't have any intelligence, but it just behaves in such a way that you think that it may be able to answer your question. And here is some sentence from them. So Eliza asked, "Please tell me what has been bothering you." The humans say, "Everything." And the bots say, "Tell me more about that." And the humans say, "Everything bothers me lately." And then the bots again say, "Does talking about this bother you?" You can see that this is just responding in a way that is like just matching what you're saying. It doesn't really have there is no meaningful conversation going on here. But this chatbot did spark a lot of debates about, like, philosophical debate about what human intelligence is and what machine is capable of. So this is one of the earliest moments that we can demonstrate that machine can process natural language, which is human language, in a way that can kind of mimic the communication between humans. And but also during this era of like 1950 to 1970s, we do not have a lot of computational power. And sometimes in science, you always think about the great things that you can achieve, but sometimes, often the case that it does not meet reality. So during this time, because of all kind of stagnation due to computing power and also other problems, we enter an era called the AI winter, in which that people lost enthusiasms in the development of AI because they were just not moving forward. But in the 1980s, that's what things started to happen again. And there was this kind of system called expert system, the occurrence of this expert system. And what it does is that a bunch of human experts can come together and say a bunch of predefined rules about some kind of a decision-making process. And the machine can use such predefined rules to make a decision. And one of the examples here is called the NYCIN. It was an algorithm that is designed to help the doctor to prescribe dosage of antibiotic for people who have bacterial infection. And what it does is basically you tell the algorithm what kind of infection it is, what kind of organism caused that, and as a result, the machine or the algorithm will tell you that what kind of antibiotic is the best and how much dosage is the best for the patient. So this is really something that this algorithm is really something incredible that we can see in the late 1980s. It just demonstrates that machine can help humans to solve some problems. But then the most important thing, which a lot of you, if you are in tech, you heard of the term backpropagation. And this is what reignited the discussion about neural network. So neural network is one of the most important things in modern AI because by constructing a few layers of neurons, we can use those to solve very complex problems using a bunch of data. So this backpropagation algorithm is really what reignited the excitement for AI. Because before, remember that I was saying that there was not much computing power, right? But this algorithm can help you to efficiently do computation in a turn something like something called gradient descent, and can calculate the weights on each neuron, meaning that you can do those calculations very quickly. So this is a really important moment in AI, the occurrence of this backpropagation algorithm. So later on, we are going into this machine learning era. So different from before. Right now, we have a lot of data. So it becomes a data-driven approach that we just put a lot of data into the algorithm and let the algorithm learn the pattern and the rules from the data without human explicitly programming what the program should do. So this is incredible too. And in 1997, IBM's Deep Blue defeats the chess champion for the first time, demonstrating that a machine can beat human in some kind of specified task. And what it does is it can calculate millions of moves when they're doing the chess here. So this is a remarkable moment of machine beating human on one specific task. And now we are moving into the kind of the modern era of 2010s. One of the most important things that happened then is this AlexNet. What it is a convolutional neural network that was that won the ImageNet competition. And what the competition was about is that you can give it a bunch of images to the algorithm, and it asks you ask the algorithm to basically identify what is airplane, what is a car, what is a cat, what is a bird. So this algorithm has incredible accuracy, I think about 99.7%. So the creation of AlexNet for image recognition really marked the beginning of the deep learning era of AI. And of course, I think a few of you may have heard this before like maybe nine years ago, when the AlphaGo, which was a product of Google, defeated the World Go champion. So this chess game, Go, is the most complicated game in the world. So just by demonstrating this kind of the result from this competition, you can see that artificial intelligence has really surpassed human in some kind of task that human may never be able to catch up with. And of course, now we are in the 2020s, and I think a lot of young people use it now on daily tasks. ChatGPT, you can ask the ChatGPT anything and give you an answer that is usually correct. I mean, mostly correct. And also you have DALL-E. DALL-E, if you don't know, is a program that you can give it text and it can generate images out of nothing. And we also have a lot of auto driving. So auto driving, like the Tesla algorithm, is also relies on the AI techniques. So here is a video that is generated by two different algorithms, and those are not real. So those are not real footage. But if you see such a video in like online or something, can you say is real or fake? Okay, so the video just demonstrated some kind of generative capability that those algorithm is able to achieve. And so recently I've been browsing some kind of like some videos or some kind of images on social media, and I realized that some of those videos are already fake videos generated by AI, and sometimes it's really hard to tell, such as like a baby taking care of a cat taking care of a baby. So logically, you think that it wouldn't make sense, that what tells you is a fake video. But if you look at the video itself, it looks like that is a real cat and that's a real baby, right? So I just want to say that you really got to be careful of what you see on the internet nowadays with all the deep fake videos, text, audio generated by AI. And one of the things that I told my parents is that if someone call you and blackmail you with money with my voice, you probably shouldn't trust them, because nowadays you can use, basically there are some programs that you can put in your voice, and then you can ask it to generate any sentences you want in your voice. And that is incredibly scary. And I think I saw some news a few months ago that someone has already been scammed by that. So the AI really has created something that is really hard to distinguish from what is real. Okay. Oh, okay. So now I've been saying AI, 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 but what exactly is AI? And this is a very good diagram showing you what artificial intelligence is, machine learning, and versus deep learning. So when we say AI, it basically mean that we are trying to create a machine or algorithm that can simulate a brain intelligence. So that is a very broad term. But in AI, we also have a subset called machine learning. So machine learning is basically extracting data pattern without explicitly programming it how to do it. So machine learning is basically you feed an algorithm a lot of data and then let it learn the pattern inside. And inside machine learning, we have a field called deep learning. So deep learning is when we use neural networks, usually multiple layers of neural networks. And that is deep learning, just using neural network. So now we have talked about some kind of AI history or what AI can be used for in real life. But why do we care about AI or machine learning in astronomy? Okay, so one trick for you to act smart is you stop saying the word AI. Instead, you say machine learning, because machine learning is what people would use if they know what AI is. But if you're using AI, then it's just like the regular, very broad term that people use in the daily life. So remember, next time when you say AI, you can replace it with machine learning to make you sound smart. Also makes you sound very professional, right? Okay, so why the heck do we care about machine learning or AI in astronomy? As we know that right now we are entering an era of big data, meaning that there is way more data that is floating into our computer or some online database at every second by some telescopes, by some surveys, or by some simulation. So those data are just way too much for some humans or a few or dozens of humans to figure out the pattern in them. And AI or machine learning can really help us to speed up that process in like detection of some kind of weird phenomenon in astronomy, or you can classify some images in astronomy, or you can do some analysis. So the main reason, to sum up, the main reason for using AI or machine learning in astronomy is that we just have way too much data and we don't have enough humans, or it's the same for like any cases in tech or something. There's just way too much data for humans to look at one by one. That's why we need the machines to make the decisions. Of course, the decision is not always correct, and neither does human always make perfect decisions. And to prove that AI or machine learning is really taking off in astronomy, I want to show you this plot. This is a plot showing the number of papers title or include the word AI in it. And we can see that there is an exponential growth. And really, AI took off around 2018 to 2019 in astronomy. So we can see that last year, I mean, not last year, like 2022 to 2023, there were about 5,000 papers published in astronomy and physics with the word AI in them. So AI has been really this new topic or new technique that people use in their research. So the first project that I want to talk about is detecting asteroids with AI. And I'm not talking about any random asteroids. I'm talking about the streak-like asteroids. So usually, when you think about asteroids, they are just some kind of rocks in space, right? So if you look at them through a telescope, they would appear to be a point-like source, which is like kind of circular or maybe irregular. But because the asteroids are kind of far away, you cannot tell if it's you cannot tell the shape. So usually they appear to be a point-like circular source. But this is the case when the asteroid is very far away and they're not moving as fast. But what happens if there is an asteroid passing closer to Earth, moving at an incredibly fast speed? Then in that case, you would not see a point-like source. Instead, you would have this kind of linear shape or a streak-like asteroids, as what I would say, in the image from a telescope. So this is, of course, this is not common because usually asteroids are not passing, I mean, not many asteroids are passing through Earth or moving at such a fast speed. But when such a case happens, we need to figure out a way to identify them and label them, and we want to calculate like what are their orbits. Are they going to hit Earth? Which is why we care about it, right? Why do we care about the asteroid that is moving fast and passing close by? Because those asteroids pose a planetary scale threat to us, and we all remember how the dinosaurs went extinct 66 million years ago, right? So really detecting those fast-moving objects is a planetary defense mission, as I would say. I mean, I would love to tell people that I do planetary defense, but that might sound too cocky. So I will refrain from saying that. But what we're doing is that we are trying to detect those fast-moving objects, and basically we want to know before they hit Earth, or whether or not they're going to hit Earth, right? Of course, I don't know how much we can do if such an asteroid is heading toward Earth with our current technology. So that's why it's very important to detect those streak-like asteroids early on before they collide, or hopefully not, with Earth. And which brings me to this machine, which called the Rubin Observatory. And I'm pretty sure every single Astronomy on Tap person has talked about this, right? Because it is the flagship mission at the University of Washington. It is, for those who don't know, this is a 8.4-meter telescope that we just recently commissioned in the mountains of Chile. So each night, so one of the trivia question was asking you how much data this telescope provides each night. The answer is about 20 terabytes. So each night, this telescope is going to pump in 20 terabytes of images data into some kind of data processing facility where astronomers around the world can just get the data from, right? Okay, so now we have this massive machine, right, which deliver, I don't know how many images each night, a lot of images each night. And the thing is that it has the largest digital camera on Earth, which made it into the Guinness World Record. So this incredible telescope is going to capture so many asteroids in its life of a 10-year mission. And I think my colleague here just told me that we're going to discover around 6 million asteroids. 6 million. And it's basically going to be almost the entirety of the asteroid in our solar system, which is incredible, right? So this machine is going to detect all the asteroids that human can reach within the next 100 years. So we have asteroids, normal asteroid. We always also have those streak-like asteroids. But one of the problems is that our current pipeline or our current algorithm is not optimized for detecting asteroid that is not a circular point. So what me and my collaborator did is that we try to use machine learning or artificial intelligence to improve the detection of such streak-like asteroids. And the technique or the method we use is called a UNet, or what UNet is basically a convolutional neural network. Okay, that term might sound kind of hard, but it was first invented not for astronomy, but rather it was invented for medical analysis, specifically for differentiating images in a, let's say, I think this is a human brain. So what it can do is it can separate what is the healthy organ and what is the tumor in the brain, or what is the different structure in the brain. So on the left here, you can see that this is what the different organ is labeled by an expert. And on the right here is completely done by a machine algorithm, by the UNet, which is quite similar in the sense that both the human experts and the UNet have detected the same kind of tumors and a healthy organ in the brain. So this technique really helps the medical people to identify the different tumors or kind of different parts of a body inside images, so which save a lot of time. So this algorithm is very good at recognizing the different segmentation of the image, which is very good for our streak-like asteroid detection project, right? Because if we can just give it a lot of data and say, all right, tell me which one is the asteroid, and we pick it out. So after some training, oh, never mind. We are going to talk about neural network. Okay, so as I said before, UNet is a convolutional neural network. What it is you have a bunch of neurons. Like I said back early on during this talk, we have a bunch of neurons, which like an on and off switch. But what happens if you put them together? Then it becomes a network, which is capable of handling more complex data structure. So this is like what the neural network is. It's just a bunch of interconnected neurons in this neural network. That is like the simple definition I can give about neural network. And this is some of our results after we train the neural network to detect the asteroids. So on the left here, this is what we say a image from the telescope. Okay, so also we did not use real asteroid in this research project. We have injected some fake synthetic source, which is some kind of look like a linear structure here into the real image to see if we can use the UNet to recover those injected synthetic source. So on the left here is the image, and in the middle here is the truth, which means that if the machine is 100% correct, then it will find this structure in it, which is like a somewhat a linear structure. And on the right panel here is what the machine recovered, which is mostly resemble the truth. But the thing is that we are not trying to be like, all right, every single pixel has to be exactly the same. Nope. We just want to say, okay, this is a linear or streak-like asteroid, and we have found it using the machine. So in this case, the machine or the algorithm has done a pretty good job in identifying the streak-like asteroid in this image. So that basically saves so much time for someone to go in and look at each pixel by pixel of the image, saying that, yep, that's not an asteroid. Yep, that's an asteroid, right? And this is another example. So in this case, we have a very faint asteroids injected here. You can probably, I don't think you can see it from the back. Maybe it's even hard to see it from the front. There is an asteroid here, and this is the truth. So this is what the machine, this is what happened if you find it 100% of the pixels, and this is what the machine finds. So you can see that in this case, even though the human may have a hard time identifying these streak-like asteroids, the machine does a pretty good job in recovering that. So we can say that our method of using AI to identify those streak-like asteroids is a success. And this plot shows you the performance of our algorithm. Okay, I don't think you can see the colors here, so I'm going to tell you what each line represents. So on the top here is the, so on the x-axis is how bright the asteroid is. We are going from brighter to fainter to the left. On the y-axis is basically how many asteroids we put in, or how many asteroids were detected by the neural network or by the UNets. So the top line on the top here is, it's supposed to be a blue line. That is the amount of asteroids or fake sources we injected into the images. So if everything worked perfectly, then we will have detected all of those asteroids like this. Like we will have detected all of those asteroids. But nothing worked perfectly, right? So right now, the old algorithm is this lower line. So you can see that the old algorithm is pretty good at detecting asteroids that are kind of bright in the brighter end on the left here, but pretty bad at detecting asteroid on the fainter end, right? But when we are using the neural network or the machine learning or artificial intelligence, we can see that there is a bump in the performance. So this is the line of the neural network. We can see that in some cases, we even increase the performance by roughly 50%. That means that if there are 100 asteroids, the old algorithm is going to detect about 25, but we are going to detect 50 using the new algorithm. So this really shows you that we have this kind of improved performance by using neural network to do this study. And remember what I said before, we are going to detect 6 million asteroids by the end of the survey of the LSST telescope. So do you think 10-20% of the 6 million is going to be a lot or no, right? So even though it does not say, it doesn't seem like the performance increased by a lot from this plot. But if you think about multiplying the percentage by the large number of asteroids we will detect, that is going to come down to an incredibly large number. So I can say that I did help to protect our planets, right? So this was this was a study led by Professor Mario Ruric at the University of Washington, also with some collaborators in Croatia and Europe. Okay, so that project is a success of detecting asteroids, right? But what about if we switch to something else, dark matter? Dark matter subhalo simulation. This sounds a little bit scary, right? So we just saw that we can use neural network for detecting asteroid, but can we use AI to learn about dark matter? Let's take a look. Okay, so quick recap for those who haven't heard of dark matter before is that dark matter is this kind of invisible matter that is in the universe that does not absorb nor emits light. So we cannot see directly what dark matter is. And so far, there has been no detection of dark matter particles. One of my undergrad professors worked in experimental physics for detecting dark matter for 20 years. And he couldn't find anything. And then he jumped to neuroscience. So that tells you how hard it is to find dark matter, right? Because we just cannot see it. We do have a lot of theories suggesting that what dark matter can be composed of. Like there's some, it could be some weakly interacting particles. It could be some very massive particles. It could be some, even could be black holes. It could be axions. It could be a lot of things. But so far, we have not detected any of the dark matter particle. And we don't know what it is. But one thing for sure is that we know it exists. And we know it exists through gravitational lensing, which is like the light bending in distant galaxies. We also know it exists from galaxy rotation curve and a lot of different methods. So this plot shows you the content of our universe. We can see that most of our stuff is made of dark energy, and about 23% is dark matter, and about 5% is baryonic matter, so which is normal matter that you can interact with in your daily life. And for today, we're going to talk about how we can study the nature of dark matter using AI for this later part of this talk. And so dark matter is pretty broad, right? We got to separate it into something that we can study in more detail. That there comes the concept of dark matter subhalo. So usually, think of this galaxy as our galaxy, our Milky Way. So usually the case is that there is a big dark matter halo surrounding us, which engulfs us in a and is extremely big dark matter halo. And within the dark matter halo, there are tens of thousands of dark matter subhalos. And the reason we call it subhalos is because they are kind of a little bit smaller. So they are a little bit smaller clumps of dark matter. That is like, we think of it as a sphere. because a sphere is the easiest way to think about it as physicists, if you heard of the spherical cow thing. So we just think about dark matter clustered together as a sphere, but of course they are not sphere. They're not sphere. But just for a simple approximation, we think about those dark matter clump as a sphere. And there are a lot of those dark matter subhalo lurking around inside a galaxy. And we can, by studying the dark matter subhalo, we can place a lower limits on what kind of mass a dark matter particle could be. So it is it's very important to study the dark matter subhalo because it helps us understand the nature of dark matter. And how do we study them, even though we cannot see them, right? Then we have to talk about dwarf galaxy and globular cluster. There is an expert on globular cluster in the audience here. You can ask him more questions if you are more interested in globular cluster later. But what those are is basically a bunch of stars gravitationally bound together, and there are a lot of them, and they are usually orbiting around our Milky Way galaxy. But the thing is that even though they look kind of circular right now, they are not going to look circular after a few orbits around the Milky Way, because the Milky Way gravitational potential is going to perturb the dwarf galaxy and globular cluster as they orbit around the Milky Way. So after some time, after some orbits, the initially circular cluster of stars would become a stream-like object, which is like what we call a stellar stream. What it is basically it's being elongated due to the gravitational pull or the tidal forces of the galaxy. So in that case, they won't be spherical or circular anymore. And okay, so remember I said earlier that there are a lot of dark matter subhalos lurking around in our galaxy, right? Now we have a lot of stellar streams surrounding our galaxy. So what would happen if a dark matter subhalo interacts with a stellar stream, right? So usually when I explain to someone, I would think about if I'm walking on a street and I got hit by something invisible, then my position would change, right? That is the same idea here. So if a dark matter subhalo were to interact with such a stellar stream, it would cause a deformation in the stellar stream itself. And that is exactly what we saw in some kind of data. So this is called the Alice-Alakuma stellar stream. So this is simulated data because we don't have too many real observational data. But what I want to look at is this kink over here. This is not usual, right? Because as I said before, if you have a stellar stream, like here, it should be like kind of continuous, right? It wouldn't have such a kink in it. By having such a feature, it suggests that it may have been hit by something else before. And we postulate that there was an interaction between the dark matter subhalo and the stellar stream, which caused this kind of kink feature in it, right? So, and the machine learning, so we don't know what kind of dark matter subhalo that caused this kink, but we know that this is the final results. So what we can do is that we can run a bunch of simulations, basically saying that we have many different dark matter subhalo with different mass, different velocity, different angles, all hitting this stellar stream. At the end, we figure out what is the best, what is like the most exact parameters of the dark matter subhalo, which creates such a kink. So we run like tens of thousands of n-body simulations, meaning that we go back in time before the stellar stream were perturbed, so it was just chilling, orbiting Earth, orbiting the Milky Way, right? But then we do some simulation that we use different sizes, different mass of dark matter subhalo to keep hitting the stream. And all of those are different simulations. At the end, we say, what is the best fit parameters of the dark matter subhalo? Like, what was the mass? What was the velocity? What was the collision angle of such a dark matter subhalo collision that could cause such a kink feature in the stellar stream? And this is not easy. Like, interpolating what the best fit parameters is not easy. And so that's why we got to use this machine learning technique called normalizing flow. So normalizing flow is it is extremely mathematical that there is not a good image that I can show for you to think about that. For the math geek out there, I'm going to say that it is a technique for you to basically evolve a normal distribution into a target distribution that resemble the posteriors. And right, so there's a lot of math that go into this technique, but it is a machine learning technique that can help us to identify what kind of dark matter subhalo that caused the kink in the feature. And as I said before, machine learning is really data hungry, and we run tens of thousands of simulations, which like a few months of GPU time on it. So astronomy could be expensive, but the cost goes to the school, so it's okay. Yeah. Okay, so what we found out is that this kink could be caused by a dark matter subhalo with the mass of 10 to the 7 solar mass. What does that mean? That means that we think a long time ago, there was a dark matter subhalo that is about 10 million times the mass of our sun that hits this stellar stream and push some stars out of its location, current locations into some kind of weird shape. So this is an ongoing project, but we are going to the final phase of publishing the paper on this technique. So what I want to say is that we are probably the first one in astronomy to use normalizing flow to study dark matter in this context. Because if you think about it, AI, this term, only became popular in the past few years after the invention of ChatGPT. So a lot of the techniques that were common in the industry or common in tech have not been fully implemented in astronomy, which means that there are so many tools out there in the tech world that we can pull and plug it into academia and make new discoveries. And that's why I'm doing all kind of projects using machine learning method, because those are still relatively new concepts or new techniques to be implemented. And those were the projects I worked on. But what about some other application of AI in astronomy? Some of them include image classification, which is classifying galaxy images based on their morphologies. Like galaxy could be elliptical, it could be irregular, it could be spiral. But there are just way too many galaxies of them and in so many images. You can train an AI to classify the images based on what they look like on the images. So this is a pretty good proven technique for classification, which was also one of your trivia question. And another thing that AI can be used for in astronomy is called like anomaly detection. And this is showing you what like AI can detect the events of a supernova, which is like when stars explode at the end of their life, based on the data taken from the telescope, because we know that different events have different characteristics. And the machine is very good at creating models for complex data. So even though there may be something that is like hard to see by human eyes, those could be easily picked up. Also, the process can be speed up by a lot when you're using just some machine algorithm. So those are pretty incredible too. But of course, AI, we say AI all the time, but it doesn't mean that we can use AI for everything, because there are some limitations. One of them is called the black box nature, which means that you know what kind of data you gave the AI, you know what kind of decision it made, but you don't know its thinking process. You don't know why it make the decision it made, which is why nowadays a lot of computer science scientists is trying to make AI a white box, like openly, more transparent, like what kind of why it made the decision it made. And that is very important, because you just don't want someone to tell you the answer without you knowing how they think, right? So also AI or machine learning is very data hungry. So it depends on a lot of data, and which means that the decision you make can have heavy bias based on the training data. So that is another caveat. And also, the usual case is that AI doesn't know the physics of our world. So it's just creating complex models by fitting the data, but it doesn't know the physics. That's why some physicists are trying to use what they call a physics foundation model, physics foundation model, which is like they're trying to train some AI that know the physics of our world, and that probably can increase the performance when they analyze certain data. And last but not least, but also there's a lot of ethical concerns and considerations when you're using AI for research in astronomy. That's why AI could be good, but it should not be overexploited. And I want to give some credits to my collaborators in the 2 research projects. And that concludes my talk. Thanks for coming. Let me know if you have some questions. Yes.
Say, oh, we trained this model, it's magic, and we got some pretty numbers that make a lot of sense.
Okay, right. That's a good question. So the question was, how do we write about AI in our research paper? So the methodology is usually we just have some citations on some CS paper, computer science papers. We're saying that this technique work, and based on some kind of previous proofs, and then we use the technique on our data, and saying that yep, this is correct. But also there is an important component, which is human verification, which is like there has to be a human comes in, go into the images or go into the data and manually verifying that what the AI is saying is true. So that is only correct for like the training phase, because as you have so much data, you won't have enough humans to look at every single of the images. You can only look at a subset of the data and saying that, yep, this meets the expectations, and we can say the AI is correct. Yep. Right. That comes back to the black box. That's why you see saw my hesitation, because sometimes there is some randomness in the AI. So you don't know exactly what it's doing, but at the end you just split out the answer. So I would say that is mostly reproducible, but the result is not going to be exactly the same. Yeah. And also another thing I noticed, from Twitter, is that nowadays a lot of AI research is on it's like based on empirical studies, meaning that they just write an algorithm saying that yep, this works, but they do not have the mathematical proof for that, which is usually not correct, right? Because you have to prove something is correct before you implement it into the real world. You cannot just throw an algorithm in the real world and say it looks correct. We should just use it without any mathematical proof. Yep. Yes. Right. So nowadays, there has been some new guidelines on using AI for research. So typically, when we publish a paper, there's going to be a statement saying that, there's going to be a statement put out by the author of the paper saying that if there was any AI assistance during the process of a research, whether it's in writing the paper or is in writing the code or in some other ways. But yes, so usually when AI has been used in a research, they're going to label it at the end of the paper saying that this research was done with the assistance of AI.
Is the concern that they take credit for a decision-making process that they may have not created on their own without giving AI credit, or is there something beyond that where like they could wreak havoc if the bad decisions made or against moving forward?
Right. And also, okay, that comes to another statement which say that the authors have agreed with all of the writings or something. Like all of the writing done or all of the data in here presented are upon the agreement of all authors of the paper. So the author would bear responsibility for what is on the paper and what is on the research. Yep. Oh, sorry. 2 more questions. ML, because it is more professional. Yes, okay, one last question. Yes. Okay. Okay. If I understand it correctly, you're asking, does the fit provided by the AI make sense in a physical way? Okay. Yes. So what the normalizing flow or the technique we use in the study, it just tells us what is the best fit parameters. But the simulation we ran, we're all using real physics and body simulation. So we took we took all of the kind of physics into account before we run the simulation. What we did is we are basically feeding a lot of different simulation of different scenarios into this algorithm, and it's going to pick out the most probable case based on the simulation that was based on physics. So the AI is not fitting the data, it's just figuring out which results is the most probable. Yeah. Awesome. All right, thank you for coming. Enjoy your night. Yep.
Okay, so since Chester is our only speaker of the evening, I'm going to give you all the trivia answers and announce the winners. And then I will release you all to go get warm, I'm guessing. Yep. Okay. Fantastic. Yeah. All right. So, trivia answers. Okay, so we had 5 groups get 7 out of 10 questions right. So they will be our winners. I'll announce them at the end. Please take 1 prize per group. Thank you. So question 1, it was John McCarthy who coined the term AI in 1955. It's false that AI, machine learning, and deep learning are all the same thing, as Chester explained. Picture B was generated with AI. I think the point is it's hard to tell. ChatGPT stands for Chat Generative Pre-trained Transformer. It was 1957 when the first trainable neural network was demonstrated. Perceptron was the name of that first trainable neural network. In a study led by the National Astronomical Observatory of Japan, AI or machine learning was able to classify spiral galaxies to 97.5% accuracy. And we can use AI in all of the things listed here in astronomy. And finally, not finally, second to finally, penultimately, the Rubin Observatory will be pulling down 20 terabytes of data per night. And finally, AOS stands for Active Optics System. All right, so the groups that are our trivia winners, the first one is JKJ. Nice. Some applause. Okay, the second one is Halions. Yeah, you guys win a lot. The third one is Artificial Influencers. Nice. Jose. Good job, Jose. Titan Uranus is the last one. All right. Very good. Okay, so please feel free to come get one prize if you want. Otherwise, we'll see you on February 26th. Thank you so much for coming, even though it's very cold out. Appreciate it.